Good day, welcome to this class. So, we would like to continue from where we stop under the rules of differentiation. Okay, this is known as the chain rule. So, we call this part D. So, chain rule arises if you have a function of the form y equal to x squared. For example, x squared plus 1. And our intention is to find the derivative of y with respect to x. Okay, so we recall that in our previous discussions, there is no such rule we can use to differentiate this, be it sum and difference rule, or product rule, or the quotient rule as well. Okay, none of them can be used to solve this. So how do we now deal with a function such as this? Okay, but here we observe that there is a function, okay, under the square root. Okay, so that's where we start from. Okay, we say let this inner term be a function u. Okay, so that y will be square root of u. Okay, so you know when the whole of the term here is u. Okay, so the whole of the term here is u. Okay, this is what this gives. Okay, and we'll call that the variable x. Okay, x squared plus 1 must be a term that is non-negative. Okay, for this y to be real. Okay, so in that case, this u also must be a non-negative function. Okay, so in our previous rules of differentiation, we have used to having a function y equal to f of x. Okay, where f is an expression of x. But here, we will now see that we have been able to deduce two functions here. One is this function and one is another function. Okay, and because of that, so this y does not go to x directly, but this y goes to u. Okay, so this y is now a function of u, which is another function inside it. And then, as you can see here, this u is an expression of x. Okay, so by comparison here, okay, this y equal to u of x is similar to this. Okay, where u is given by this term. Okay, so in our elementary mapping, we refer to this as a composite function. Okay, so in this case, we'll say this f is a function of the form f of u. Okay, which means a composite function, and this literally means what we have here. Okay, so but the aim of this class is to show us how to what is chain rule and how do we use chain rule to find the derivative of a function, of a composite function. So let's define this, after which we will consider some examples where the chain rule can be applied. So the chain rule now, if u is differentiable, okay, we have considered u as a function, okay, but here we are saying if u is differentiable at x and f, okay, which is an expression of u, okay, is differentiable at u, okay, such that there is a function y which is a composite function. Okay, and that y is given as this y equal to f of u. Okay, here we will know that, okay, by virtue of what we have above here, u is dependent on x, okay, and this function y or f is dependent on u. Okay, so if you have this, okay, so then the derivative of y with respect to x will be the derivative of y with respect to u, okay, multiplied by the derivative of u with respect to x. All thanks to James Gregory in the early 17th century, okay, who give us the approach or formulation for finding uh, the slope of a composite function like this. Okay, so let us have a non-rigorous proof of this. How do we arrive at this? Just a skeletal proof of what we have here. So just like we have in the rule, say suppose u and f are differentiable at x and y, at x and u respectively. Okay, that is, u is differentiable at x, y, f is differentiable at u, as we have it in the rule. Okay, so for which these two functions are associated this way. Okay, so the derivative of y, okay, by definition means the limit. Okay, so we recall that we have been using h to mean delta x in our previous video. Okay, so let's maintain the, instead of writing h here, let it be delta x. Okay, so literally the derivative of y with respect to x means changing y over the changing x. Okay, this is what this means. Okay, so since y is a function of u, okay, so this is nothing but okay, since this is dependent on u, okay, you can initiate the term delta u, okay, and this delta u again will be with respect to delta x, or accordingly we'll see that okay, this actually gives this actually. So according to the limit law, okay, we can distribute this limit on each of the derivatives that we have here, and this will be the limit of the derivative of this. Okay, so here this will be delta u. Okay, it is delta u because as delta u tends to 0, compulsorily this delta s also goes to 0, since u is depending on x. Okay, and this will be the limit delta u delta x as delta s goes to 0. Okay, so don't let us confuse with this. Okay, this, since this is tends to 0, this always tends to 0. Okay, because u is a function of x. Okay, so by definition, what this means is, as you can see, if you consider the total derivative of this becomes dy du, and this becomes du dx. Okay, this is just a non-rigorous proof. Okay, so in a case where we have more time to discuss the proof of this, okay, so we will do that. Okay, but let us have it as it is given here for now. So let's see some of the examples, okay, that are in line with the chain rule. Let us first consider the example we have earlier, which is if you have to differentiate the function y equal to the square root of x squared plus 1, okay, with respect to the argument x, with respect to the argument x, okay. So as I said earlier, so this is the linear function. So let u be the linear function, okay, and then y we equal to square root of u, okay. So therefore, from the formula, dy dx is dy du multiplied by du dx, okay. And accordingly, when we substitute the term that we have above here, this is the derivative of u with respect to u multiplied by, when we replace u here, this is x squared plus 1 dx, okay. So when we differentiate square root of u with respect to u, okay. So we record that this square root of u literally means this, okay. So if we differentiate this using the power law, this half will come down and then we will remove 1 from the power, okay, and this will be multiplied by 2x, okay. So since the derivative is with respect to the variable x, okay, so the term u here will be replaced, okay, to its original form, and this will be, okay, and we'll see here these two cancel out these two, and we are left with x, okay, which is coming out here, multiplied by x squared plus 1 raised to the power of this, okay. So here is the slope of the function we have here, okay, and we are able to do this using the chain rule. Let us look at another example. So let's say example 2. So if you have to differentiate the function y equal to exponential sine x with respect to the argument x, okay. So looking at this critically, again, we'll see that this sine x is an inner function, and that's where we start from, okay. Again, we say let u be equal to the inner function, which is sine x, and this y will be exponential u. So therefore, the slope dy dx is equal to dy du multiplied by du dx. Accordingly, this will be derivative of exponential u du multiplied by the derivative of sine x dx, and this will be exponential u multiplied by cos x, okay. Again, we replace u, okay, as this, and this will be, okay. So we'll bring cos here, okay, since under the product commutativity hold, okay. So this will be cos x exponential sine x. So here is the slope of this function y equal to exponential sine x, okay. So let us see another intriguing examples, 2 of them. So these functions actually look alike, but in the actual sense, or when we graph the 2 functions, they are not the same. Okay, so if you are asked to find the slope, let's call this number 3. So we'll group this into 2. Okay, just to see the comparison of the slope. If you have to differentiate a, y equal to cos square x, and b, y equal to cos x squared. Cos x squared. Okay. So with respect to the argument x. Okay. So one may want to confuse this to be the same, but literally they are not the same. Okay, because this first function is the square of all this. Okay, and this b actually means cos of x squared. Okay, so and they are not the same. So by graphing, by what have you, they are not the same. So and accordingly, since they are not the same, their slope will be different. Okay, so let's take them one after the other. So let's discuss the slope of A here, while the slope of B here. So from A, they are given y equal to cos square x. Okay, so if you look at this, we see that the nav function here is cos x. So we say let u equal to the nav function, which is cos x, and here y will be u squared. Okay, so you can see u is this inner function. Okay, the main term will be u squared, which is this. Okay, so therefore we cannot find the derivative of y with respect to x. Okay, and this will be equal to, as we have it in the formula, dy du multiplied by du dx. Okay, so but here we have y to be u square du multiplied by du dx. Okay, u here is cos x divided by dx. Okay, so we differentiate this with respect to u. This will be 2u multiplied by minus sin x. Okay, differentiation of cos x. Okay, we have known this to be minus sin x. So again, this is so we'll place u here to get this. Okay, so other than the true identity, okay, 2 cos x sin x means sine 2a. And accordingly, okay, you can say the slope of this is minus sine 2a, minus sine 2x, sorry. Okay, so according to the true identity, this sine 2x means 2 cos x sin x. Okay, so whether this or this, okay, no, that is correct. Okay, so this is the slope of this function. So let's see from the part B what the slope of this function is. Okay, in part B we are given y equal to cos x squared. Okay, so as seen here, okay, the inner function here is 0. Okay, and the y will be cos u. Okay, so therefore the y ds, which is the derivative of y with respect to u, okay, that will be d cos u. Okay, du dot du here, u is given as x squared dx. Okay, so accordingly, when we differentiate cos with respect to the argument u, this is negative sine u. Okay, multiplied by differentiating x squared with respect to x is to x. Okay, so we can now replace this u again. Okay, recall this u is given as x squared. Okay, so we can write this. Okay, since commutativity holds there, okay, we can bring this 2x forward, so that this should be negative 2x sine x squared. Okay, sine x squared. So let's write this properly. Okay, so if you compare the slope, Okay, either this or this, you will see that these are not the same. Okay, these two functions are not the same, and if you look at the slope are not the same. Okay, so let us now look at the case of a chain rule versus the power rule. Okay, so the case where we use both the chain rule and power rule concurrently. Just to state it, and then we consider few examples and that too. So it's a subtopic under the chain rule. The chain rule versus the power rule. Okay, just like we have it earlier. Okay, if u is differentiable as we earlier postulate, okay, and f okay, if u is differentiable at x and f is differentiable at u. Okay, so for which y is equal to this. Okay, okay, so sorry, so let's change the marker. So this marker is not giving us a good so for any positive integer, okay, n, so if you have that this y is equal to f, which is the expression of u, and this u is raised to the power of n. Okay, so if this function is given as this, okay, you will recall that this function is we have discussed under the chain rule, and then we are now including a power, okay, a power n where n is a positive integer. Okay, so in this case, we see the derivative of y with respect to x, okay, is given by, okay, applying the power law to this, okay, which says whenever we have a function whose power is n, this will be this n minus 1. So according to the power law, we take n down and then remove 1 from n. Okay, so by the chain rule, okay, this will be multiplied by the derivative of u with respect to x. Okay, so this is where we have the chain rule and the power rule are being used concurrently. Okay, so there are many examples of this form, so let's take them one after the other. So if you ask to differentiate the function y equals to x cube minus 1 raised to the power of 10. Okay, of course, with respect to the argument x. Okay, so here, if you compare this with what we have earlier, this function is a function u, okay, whose power is n. Okay, so by comparison, so this is u of x. Okay, of course, this is this. Okay, so to let u of x equal to x cube. Okay, so the power law, for the power law, okay, we have that dy dx is n u of x is the power of a minus 1 du dx. Okay, according to the power law, this n here by comparison is 10. Okay, u of x remains this, which is x cube minus 1. Okay, and remove 1 from the power, this is 9. Okay, so multiply by u. If we differentiate u with respect to x here, okay, so this becomes 3x squared. Okay, so accordingly we can multiply this together to have a more compact form. So this 3 times 10 here is 30. Okay, so x squared multiplied by x cubed minus 1 raised to the power of 3. Okay, so this is what we have here. Okay, so here is the slope of this function, and this is how we apply the chain and the power. So let's also have one more example of this, okay, before we round this up. Okay, so if you have to differentiate the function, okay, this time let's use a different variable, t over 1 plus t. Okay, this time the argument here is t. Okay, the argument here is t. Okay, we want to find the derivative for this function with respect to t. Okay, and this will be, and of course, by comparison here, we see that this is a term u. Okay, so let u equal to t over 1 plus t. Okay, and of course, we need to know what is the udt. Okay, so but from here, okay, we'll see that to get the udt, we'll apply what we call the quotient rule. In our last video, we have discussed that extensively. So let's see. Okay, let's see that from here. So if you say this numerator is a and this denominator is b, okay, so the formula for finding the derivative of u with respect to t will be b dA dt minus a dB dt over a b squared. Okay, accordingly, so substitute all this time into this formula. Okay, we'll be able to get the derivative of u with respect to t. So let's do that. Okay, here we have b, which is 1 plus t. Okay, so dA dt, from here we should differentiate this t with respect this a with respect to t, that is 1. Okay, so this is 1 minus this minus from the formula, so a, which is t, multiplied by dB dt. Okay, differentiate this again with respect to t. Okay, so this is also 1. Okay, so everything is over 1 plus t, that is b squared, that is 1 plus t all squared. Okay, so if you open a bracket here, okay, t times 1 is t. Okay, this 1 does not affect this, so this becomes the t cancel t there, so the main term here will be 1 all over 1 plus t all squared. Okay, so this is the derivative of u with respect to t. Okay, so now let's now apply the power law, then we multiply what we have here. Okay, so here the slope you are looking for is the y dt. Okay, and we want to apply the power law. Accordingly, when the power law says this is m u of t, okay, call it u of t because the argument here is t, okay, n minus 1 du dt. Okay, so if you recall, if you compare this with the formula, this n is 7, okay, and replacing this is 1 plus t. Okay, if you 7 minus 1, that will be 6. Then multiply by the udt, which is this. So this is 1 over 1 plus t squared. Okay. So let's shift this somewhere so that this will be, this is equal to 7 into t over 1 plus t is power of 6 multiplied by this, which is 1 over plus t squared. Okay, I think this is okay now. Okay, so you can simplify this further to have a more compact form, and this will be equal to, okay, if you apply law of indices here, okay, we'll see that this is 70 squared. Okay, this power goes for this and it's also good for the denominator. Okay, and this will be 1 plus t is the power of 6 multiplied by 1 plus t raised to the power of 2. Okay, accordingly, this is 7t squared over 1 plus t. Okay, by law of indices, you can combine this to get this. So here is the slope of the function y equal to t over 1 plus t is to the power of 7. There is the slope. Okay, so this is how we apply both the chain rule and the power rule. Okay, so we can now give some exercises, okay, for you to lay your hands on. You can try this at your leisure time after watching the video on the chain rule. Okay, so let's have them one after the other. So differentiate the following. Okay, so use the argument, the same argument throughout. Okay, but you can use any other argument. Okay, for sake of, you have a function like this. Okay, you find the slope of y with respect to the argument x. Okay, throughout. Okay, so 2. Okay, if you are given x, okay, let's say y equal to 1 over 2t plus 1 is the power of 3. Okay, then we can apply quotient rule to do this, but we have wanted to use this chain rule to also do this. Okay, so 3, the function, the cube root of exponential x plus 1. Okay, exponential x then plus 1. Okay, and the square root. So if you find the derivative of this with respect to x. Okay, so let's add one more, or 2. Okay, so if you are given a function y equal to tan of x cube. Okay, so let's make this number 4 and number 5. Okay, let's have the function x squared minus 4x plus 3. Okay, raised to the power of 10. Okay. So at your leisure time, you can try all this. Okay, and if you have any question regarding any of this, okay, so let me know in the comment section. Okay, so we'll try to attend to them one after the other. So thank you and have a lovely day.